We have slowly been learning different aspects of distributions, more specifically the normal distribution, which ideally is going to be the type of distribution that describes a lot of the variables that we're interested in. Again, that's not always going to be the case. We've discussed some that do not follow a normal distribution that many times will be things of interest. Like in my case, again, I studied domestic violence and perpetration of abusive behaviors doesn't function in a normal distribution. So there will be some instances where, again, the normal distribution will not be the most appropriate. But again, a lot of the psychological phenomena that we're interested in does follow a normal distribution. And as such, a lot of the things that we've been learning about normal distributions apply to how we analyze data that, again, has to do with psychological phenomena that has that type of distribution. Now, today we're going to learn about C-scores, and we're going to see how C-scores are going to help us not only understand different aspects of the distribution itself, but eventually how we're going to use this type of information to start making inferences about whereas we have significant findings or not. Before we get started with C-scores, we're going to very quickly review the normal distribution, some of the things that we already are familiar with, and other newer pieces of information that are being presented for the first time here. Now, the normal distribution can look different depending on the mean and the standard deviation. So we'll have the normal distribution looking differently. For instance, here on the corner, you can see three different types of distributions. Technically, all of these types of distributions are the same type of distribution, which is a normal distribution, but they still have, to an extent, different shapes. And primarily what we see again is that they're differing in height and they're differing in width. The height of the distribution is based on the mean. Why? Because we've discussed before that at the peak of every distribution, we're going to have the mean of that distribution. Why? Because it's going to represent the highest bar that exists in this distribution. Remember that we do draw these distributions just with these lines, but under the lines, we have a distribution of bars that are creating this specific shape. And again, the higher the bar, the higher the frequency that value is being shown, which is going to, again, ultimately be the best descriptor of the mean. So at the peak of every single distribution, we will always have the mean. But as you can tell, the mean is going to change differently depending on how much or what the frequency is for each one of those specific variables. The other thing that we see different again is going to be the width of those distributions. And we've talked in different lectures about how like the width of the distributions are an observation or a measure of variability. And again, one measure of variability is going to be the standard deviation. So the standard deviation is going to dictate how wide or narrow the distribution itself is going to be. But what is still remains true, irrespective of these distributions having a different mean and a different standard deviation, is that if I draw a line in the middle of these distributions, and I'm doing my best here to draw a straight line, obviously, kind of failing here. But if I draw a straight line down these distributions, we should still see that all of these distributions are still symmetric around the mean. So again, I'm going to locate the mean, which is at the top of these distributions, which is the peak of these little mountains. I like referring to them as mountains. And if I follow again that point down, both of those sides of the distribution are going to be similar to each other. They're going to be these mirror images that are descriptive of the normal distribution. So again, they will look differently because each distribution has a different mean and standard deviation, but at the end of the day, there are still normal distributions because they are symmetric around the mean. Other things that we've discussed before is that the mean, median, and mode are equal. Excuse me, here's a little misspelling, but they are equal. So again, if the mean of this is, I don't know, 15, then the mode is going to be 15, and the median is going to be 15. So anytime we have a normal distribution, the mean, median, and mode are going to be equal. The other thing which we haven't really discussed yet is that under the curve, so when we're considering these lines, so under these lines, we're going to have bars or a number of scores that are going to add up to 1. And this is in reference to specific percentages that we're going to see on the next slide, I believe, where again, if we add up all of the percentages, then these are going to add up to 100% of the area. So again, what it's saying is that we're going to be having these bars that are represented by those lines. And at the end of the day, when we add up all the scores that is represented by each one of those bars, we're going to see that is going to equal to 1.0 or 100% of the area. So that's what that is in reference to. And the other thing that we have here is that for normal distributions, they're going to be denser in the center and less dense in the tails. So again, what that is saying is that we're going to have the majority of the scores located near the mean, because remember, the mean is a representation of the typical score of a distribution. So most of the scores are going to be closer to the mean. So the majority of the scores are going to be in the mean. And again, if we were to draw bars, we're going to see that the bars are going to be higher around the area of the mean, which is again representing higher frequency, whereas in the tails, we're going to have a lower number of scores that are going to be located there. And again, those are going to be represented by very small bars. So the height of those bars are going to be smaller in comparison to the bars that we will see towards the mean. When we have a normal distribution, again, because it follows a very specific pattern when it comes to this symmetry around the mean, we know what are the proportion of scores in each part of the distribution. So specifically here, you have a distribution that is broken down into different percentages. And those percentages, again, are representing the amount of the scores, of the total scores in the distribution that are within that specific region of the distribution. Now, just to make it really clear, this 34% here is representing any scores that is falling right here. So this is basically a bar. And again, anything that falls here is going to be 34% of scores. Now, one thing that I want you to notice is that this is falling between the population mean. This is a notation we've talked about before. So this is representing the mean of a population. And then it's the width or the distance from this mean to one standard deviation. Remember that the standard deviation is a measure of distance or an average measure of distance of the distribution scores or the scores that exist in this distribution. So 34% is within one standard deviation below the mean of the population. So towards this direction, we have 34%, excuse me. On the other side, on this other bar, we have another 34%. And we have a very similar picture. We have the population mean right here. And on this side, we also have one standard deviation. So within this width, we have another 34%. So what this is saying is that 68% of the scores, which is 34 plus 34, so we're representing this entire area right now, is within one standard deviation from the mean, and that is either below the mean or above the mean. But again, we're within one standard deviation of this particular scores. Let me clean this up now. Oh, sorry. Then the next thing that we know is that we also have 95% of the scores, or approximately 95% of the scores within two standard deviations. So we're going to be looking, so this is the population mean. We have two standard deviations right here, So we're going to be looking at this entire area right here. And I'm just gonna try to color this as best as I can. But if you were to add up this 34, this 34, this 13.6, and this 13.6, you would get approximately 95% of the scores would fall in this area right here. Now, for the normal distribution, we technically label it up to 3 standard deviations. Right here again, you see 2 standard deviations, 2 standard deviations. We're going to have 3 standard deviations somewhere here and 3 standard deviations somewhere here. Now, we're going to add a negative sign here. All the negative signs are representing is whether they are below the mean, which in this case again is the mean, or above the mean. Anything that goes from the mean to this side is above the mean. And then anything that goes from the mean to this side is below the mean. Now, why? Because these scores from here to here are going to be higher than the mean. Remember that this is the x-axis, and it's typically going to be in increasing order. So going up here, this way again, we have higher values. Going the other way, we're going to have negative values. So this is above the mean, this is below the mean. But again, we have up to 3 standard deviations. In 3 standard deviations, we're going to have like 99.9% of the scores. But whenever we're doing some of our calculations for statistics, or some specific statistics, so that we can see if our findings are significant or not, we're going to be using this knowledge of the way the scores are distributed to make those decisions, because anything that is in this area that I'm painting red is going to be, and you can see the percentages here. So if you put these percentages together, you're going to have approximately 5%. This 5% of scores, we're going to refer to them as extreme scores. And what these extreme scores are representing, they are scores that are most likely belonging to a different distribution, a distribution that it's not represented by the scores that we have right here. So again, this have their own distribution. And when we have something like that happening, we'll be able to decide again whether our findings are significant or not. Now, we will have more of a full lecture on this, but it's good for us to keep in mind already where are we moving forward to with some of this knowledge on the distribution. So again, 68% of the scores are within one standard deviation. About 95% of the scores are within 2 standard deviations. And again, we're working with 100% of scores, right? So about 95%, that's already covering a big area of the scores. And then we have another 5% of scores that will be considered extreme. And again, depending on where our overall score falls, we're going to make decisions whether our findings are significant or not. But again, more to come on this in, I believe, the next chapter. Okay, so how do Z-scores play a role in the normal distribution and how do we specifically use them? Well, first, a Z-score is going to be a standardized score that is going to indicate the location of a score within a distribution. So it's going to tell us the distance from the mean in standard deviation units. And the sign of the score, similar to what I explained before, whether it's positive or negative, is simply going to tell us if the score is above or below the mean. Now, the reason why Z-scores are extremely powerful and useful for us is because, again, different distributions are going to have their own mean and their own standard deviation. So we're not able to make comparisons to each other if we don't have something that is similar. So think about it as like currency, like monetary currency. You can talk in dollars or in pesos, and again, they'll probably relate to each other, but we don't know how they relate to each other unless we have like a common coin so that we could make like specific comparisons to each other. So that Z-score is going to be this kind of like standardized currency that will allow us to actually compare two scores that are coming from two different populations. So again, populations meaning that they have their own distributions. Distributions that have their own mean and their own standard deviation. So again, once we calculate this Z-score, which we're going to use the mean and standard deviation of the distribution of that score, then we're going to be able to make the comparison across different distributions. Now here you have a normal distribution and you have the x-axis labeled with the Z-scores. You're going to see that at the mean, which is again always at the peak of the distribution, you have a Z-score of 0. This is always going to be the case. The mean of a distribution, or a normal distribution, it doesn't matter what mean that is, if it's 2, if it's 4, if it's 10, if it's 20, if it's 50, it doesn't matter what that mean is. As a Z-score, that mean is always going to be represented by 0. Why? Because in the previous slide, I mentioned that the Z-scores are moved in standard deviation units. And standard deviation is the average distance from the mean. The mean is at the mean, so there is no distance at all. So in this case, this is going to be 0. Now again, we have this that is plus 1, plus 2, minus 1, minus 2. Before I get into what those mean, remember that this negative sign or this plus sign, all it's saying is if it's above the mean, which means again we have higher scores, or if it's below the mean, which means that we have lower scores than the mean. But they're also moving in standard deviation units. So this from here is 1 standard deviation. And then from here to here is 2 standard deviations. So if I were to draw the standard deviation units here, so I'm going to do standard deviation here. We're also going to have a 1. We're going to have a 1 SD. And again, it's positive only because it's above the mean. And then 2 standard deviations right here. 1 standard deviation below the mean. So we're going to add that negative. And then 2 standard deviations right here. So the Z-scores again move in standard deviation units, So if we wanted to, again, label our distribution with z-scores and standard deviation, then it would look something like this. It would follow exactly the same pattern from 2, 1, 0, 1, 2. Again, technically we have up to 3 because 3 would give us or bring us to like 99.9% of the scores. But they'll follow the same pattern. So here again, we'll have those 3 standard deviations or plus 3 standard deviations. And this pattern is very important for you to learn. Make sure that you learn how this pattern looks as well as the percentages that we discussed earlier, because again, you will be tested on those. Okay, so let's go ahead and look at one distribution and see how, again, the z-scores, the raw scores, the standard deviations, all of those things kind of come together when it comes to, again, a normal distribution. Now, here, the type of distribution that we're seeing, it has to do with IQ levels for children specifically. Now, again, some important things to note very quickly. Let's first understand or remind ourselves of how the normal distribution kind of looks like. Right here, again, we have our x-axis, which in this case is representing the IQ scores for children going from 0 to 150. So again, it's very typical that when we have our normal distributions, we have this like increasing order in values, which is why, again, we say that anything above the mean is higher than the mean and anything below the mean is lower than the mean. We'll get back to this in a second. If I were to draw this distribution, again, it will look something like this, which again is creating that kind of bell shape that has a peak and it has 2 tails. So the peak is going to be right here, which again is going to represent the mean of the distribution. So the mean is usually at the peak. So in this case, the mean is actually at 100, and we can see that because it's at the middle of the distribution. So the mean is equal 100, which is in this case representing IQ. So an IQ of 100 in children is the mean. Again, anything towards the right of this mean is going to be above the mean, or is considered above the mean, because all of the scores, like 125 or 150, they're going to be higher than the mean. So again, they're above the mean. They're going to be higher. From this point down, this is considered below the mean because the scores are lower than what the mean is. So again, if the mean is 100, which again we can see right here, 75, 50, 0 are going to be below the mean. So again, this is how that kind of works or looks like when we're considering things that we already know about the normal distribution. Here on the other side, we have the y-axis. In this case, it's representing the number of children that are scoring at each one of these levels of an IQ. So again, we are assuming they were tested and we have their scores on those exams. Remember that the height of the bar is representing the frequency. So we're going to see where this bar is hitting on the y-axis, and that's going to tell us the frequency. So in this case, that probably represents maybe like 30 children who got an IQ score of, I don't know, it looks maybe like 60, an IQ of 60 or something around that. Let me go ahead and clean this up. So again, some quick reminders about how we read this information, because again, we're going to start getting closer and closer and closer where all of that information is actually going to serve us to be able to say if findings are significant or not. Now, another thing that I want to point out is this value or label right here. This is label mean. All of these numbers that we can see here, 0, 50, 75, 100, 125, and 150 as the raw scores. And what the raw scores mean is this is exactly as they were measured from the participants. So no changes have been made to this at all. No transformations, no anything. So we say raw scores because again, they're raw. Nothing has been done to them. So if you think about like cooking meat, if you have raw meat, again, this is in the most natural way it came and nothing has been done to it. Now, eventually, maybe you add some seasonings, you cook it up and all that kind of stuff, and then transform into something else. So the raw scores, again, is just simply representing how the scores from participants originally came in. Eventually, what we're going to be doing today is that we're going to be transforming these raw scores into Z-scores. And we're going to see that at the end, when we finish these transformations, because this is a normal distribution, we're going to end up something like this. 0, +1, +2, -1, and -2. Again, the negatives and the positives, which I'm including now, the negatives and the positives are simply saying above the mean, below the mean. That's all. And the actual Z-score number, the magnitude, is just telling us how far away are those scores in standard deviation units from the mean, which in this case, again, is 100. Now, specifically to this table, again, we are aware of what the mean is, which is going to be this 100 right here. Again, because that is at the peak of this distribution, that is going to be the most typical score that is showing up. Now, we technically do not know the standard deviation yet, or at least in the previous slide, we didn't really know the standard deviation. But here, we're being told that we have an IQ score of 115. And then now, with more certainty, we're being told that this is equivalent to a Z-score of 1. So this is telling us that this score is one standard deviation above the mean. So now we know the mean, which is 100, and the standard deviation, based on this information that we have here, is 15. So actually, the 1 or a Z-score of 1 is going to fall right here, which is equivalent to an IQ of 115. And now that we have this information, we should be able to properly label all the other scores to be, again, 2 Z-scores, 3 Z-scores, or -1 Z-score, -2 Z-score, -3 Z-scores, and so on. And again, when we're working with raw scores that are moving in perfect standard deviation units, so in this case by 15 units, we'll be able to calculate those Z-scores very quickly because they follow a specific pattern. So I'm just going to show you a couple of slides that are going to follow this. So now here we have an IQ of 130. We already made the assumption that the standard deviation is 15 based on the information that was given to us in the previous slide. And we can see that 130 is going to be 2 times 15. So this should be a Z-score of 2 because it's moving 2 standard deviations above the mean. So here now we can see that that's actually the case. Again, if the standard deviation is 15 and this is 130, our mean is 100, this is 2 standard deviations above the mean, so this is going to get a Z-score of 2. And we're going to keep seeing a similar pattern. Now here we have an IQ of 145. Again, the standard deviation is 15 15, 145, or specifically this 45 because the mean is 100, is going to be 3 standard deviation units because 3 times 15 is 45, so this should be a z-score of 3. So again, if I were to ask you what is the z-score of this, and we have already established what is the mean and the standard deviation, we should be able to make this calculation very quickly, which is going to be, again, 3. And we can do exactly the same thing going backwards. The only thing to keep in mind here is that, again, we're moving now below the mean. So this means that any scores that we calculate below the mean are going to be negative. In the case of 85, we can see that the difference between 100, which is the mean, and 85 is 15 units. And we already said that our standard deviation is 15. So it's still moving in standard deviation units, but now it's moving backwards. So an IQ of 40 or 85, excuse me, is going to have a z-score of -1. And then if we have an IQ of 70, again, this is a 30-point difference. If we are looking into that in standard deviation units, each standard deviation is 15 units, so that is 2 standard deviation difference. The z-score should be equal to 2.0, or a z-score of 2. And again, this is going to be negative because we're moving below the mean. So again, in this case, the z-score would be -2. And then here, if I give you a number of 55, again, this is going to be a 45-point difference. We're moving below the mean though, so this z-score should be negative. And again, in this case, we're going to have -3. So again, this is going to be a very similar pattern that we're going to see consistently in normal distributions. Whatever the scores are, your z-scores will always look like this because we're always considering the mean and the standard deviation of the distribution to transform these raw scores into z-scores. So the z-scores will always follow this pattern. In this case here, we have a z-score of 0 for the mean because we said the mean is always at 0. Or it's always at the mean, which means there's no distance between the mean and the mean, so it's going to have a z-score of 0. So again, here we're seeing this, where the z-score that we're being asked about is going to be at the mean, so it's in this case going to be 0. So again, this is your typical spread of z-scores when we have raw scores that are moving in perfect standard deviation units. Again, this is a good pattern to learn because you'll be using this for your homeworks and your exams. Now, typically, again, we can make those calculations very quickly if we know it's a normal distribution because the z-score is going to follow a very specific pattern as we just saw. But that is only for the values that move in perfect standard deviation units. If we don't have one of those, then we can still make an educated guess of what is the z-score, but if we want something more precise, then we need to use the formula. And the formula for a z-score, and this is going to be very important for you to, again, write down somewhere and make sure you memorize, is going to be z-score equals deviation divided by the standard deviation, which is the same thing as the raw score minus the mean divided by the standard deviation. So again, if the z-score is a value that provides us the position of a score in the distribution, it makes sense that we're going to be looking at the mean, or that we're going to be using the mean and the standard deviation of the distribution, because both of those have to do with what shape the distribution is going to take. So again, we're going to get our raw score, which is the score that we get from our participant without doing anything to it. And then we're going to use these two properties of the distribution to calculate a z-score that will tell us where this raw score specifically is located in that distribution. Now, both of these formulas are exactly the same, so you can use whichever one is the easiest for you to remember. Deviation is just the distance of the raw score and the mean. So this is equivalent to this right here. So again, these are identical. Whatever is easier for you, go ahead and use that. So again, let's go ahead and consider that maybe we want to get the z-score of a value that doesn't perfectly fall in standard or doesn't perfectly move in standard deviation units, as in like full standard deviation units, which in this case could be 120. So we can still make, again, an estimate of what is the z-score, because if we know what the pattern is in a normal distribution, such as this one, and we have already this label, we see that this IQ of 120 is going to fall between a z-score of 1 and a z-score of 2, because it's within this area where we already know those two z-scores. Now, it is closer to 1 because it's going to be like somewhere here than it is to 2. So if we had to take a guess, maybe we would say this is like a z-score of 120, 130, or something like that. Here we have a similar case. We have another score that we would want to know the z-score from. So we're going to do something similar. Again, if we know how this pattern looks in a normal distribution and we have this kind of information, again, in this case, now we know that this z-score is going to be between 0 and -1, because this value of 90 is falling somewhere here between these two. So if we had to take a guess, maybe we would say like negative 70 or negative 60, because again, it's falling between a z-score of 0 and a z-score of -1. So we could make those estimates, but typically when we're doing science, we want to be as accurate as possible. So rather than just guesstimating, we're going to want to calculate the real z-score. So here I've given you a table that is going to be very similar to things that you would see maybe in your homework assignment, maybe on your exam. In one way or another, I guarantee you're going to be asked to calculate a z-score. Now here I give you the information for the distribution, which we've been using so far. We have a mean of 100 and we have a mean of, a standard deviation of 15. So you have the information that you need so that you can get these raw scores and transform them into a z-score. Remember that for z-score, you can either have deviation, and please excuse my writing. I'm writing directly to the computer, so it's kind of hard to do that with a mouse. But this is going to be deviation divided by the standard deviation. So the standard deviation, you already have it right here. So all you're doing is substituting that number in this formula. But you can also use this other formula, which is exactly the same thing. It's just the deviation is spelled out a little bit more, which is going to be, you have a raw score minus the mean divided by the standard deviation. And all these three pieces of information are given to you. You have the mean right here, you have the standard deviation here, and you have the raw scores here. And all you have to do is make those substitutions where it belongs to. So here we have one first example. We have a raw score of 115. So 115 goes in here. Minus 100. 100 is the mean. So again, we have raw score minus the mean. So the deviation, which again, the deviation means raw score minus the mean, is going to be 15. And then we have the z-score, which is going to be deviation divided by standard deviation, or again, a fuller formula would be this. You're going to have 15 divided by 15, that's going to equal 1. And if we were to go back to the slides where we were forming or populating our z-score x-axis, you'll see that it was actually equal to 1. So go ahead and pause the video here. take a couple of minutes to transform all of these raw scores into z-scores, and then we'll come back on the next slide where I have the answers for you. So hopefully you came up with these answers. And hopefully you also noticed that this were some of the values that we had already worked with when it came to those graphs that I was showing you. And those were the values that we had kind of visually calculated. But again, just so that you can see that they actually would fall within those z-scores. Now, these last two were the ones that they weren't moving in like perfect standard deviation units. So it was a little bit harder for us to tell what the z-score was. We could, again, guesstimate, but we want to be as accurate as possible, right? So the z-score formula comes very handy when we cannot just simply guess the z-score by knowing the mean and the standard deviation. And we might need a little bit more of a calculation here. And again, we had a 1.33 for a raw score of 120, and we have said that the score had to be for sure between 1 and 2 because that score was falling between that range. And then for the next one, we had a negative 0.67, and again, we had already talked about how the score needed to be between 0 and negative 1. So this calculation seems to go along with what we know about a normal distribution and how the z-score pattern shows up in that type of distribution. Now, the normal distribution has already been looked by someone, and they have calculated all the proportions that would be equivalent to specific z-scores. So this is what we call the unit normal table. And again, this table will allow you to locate a specific z-score and then tell you the proportion of scores that is represented by that z-score, considering that this is in a normal distribution. So we can only use the uninormal table to do this if we are working with a normal distribution. And if you have to do that, it will look something like this. Again, you have a table where in one of the columns, you're going to have the z-scores. So if you were to be interested in a very specific z-score, then you can go down this column, choose that z-score, and then see what is the proportion of scores that are going to be representative by that z-score. So for instance, for a z-score of 0.30, we're going to see that we're going to have 0.6179 that will be represented as like that will encapsulate that z-score of 30. And then the rest of that is going to be considered to be in the tails. So that is everything else that is left over that is not represented by a score of 0.30. Now, one important thing here is to remember how to change your decimals to percentages because this decimal point is going to be representing 61.79% of the scores. And sometimes, again, it's easier for us to understand in percentages, because again, in this case, it will mean that 61.79% of the scores in the normal distribution are at a score of 0.30 or lower. And 38.21% of the scores in the distribution are at a z-score of 0.30 or higher. So again, if we have a normal distribution like this, and we have a score of 0.30, so let's say right here, 0.30, what this is saying is that this portion right here, this is the 61.79%, which means that we have scores that are scoring exactly at 0.30 or below 0.30. So again, this 0.30 of the distribution is going, or this z-score of 0.30 is going to cut the distribution right at that point, and is going to tell us that it represents this scores right here. But again, whatever is left over, which is this, is going to be any scores that are higher than 30 because again, they're going to be above the mean. And they're considered to be the tail because those are the scores that maybe we're not paying attention to necessarily, that are not being described by this Z-score. Okay. So now this is going to lead us to a specific concept or a specific type of distribution that we haven't really talked about much. So we've talked about distributions in general, but now we're introducing here the distribution of sample means. We'll talk a little bit more about this on the start of the next lecture, but it's still a distribution. So we're still working with a distribution that is going to be normally shaped. The specific thing that is unique about this is its sample means. So the type of scores that are going to go into this distribution are the means of individual samples. And again, we're going to talk a little bit more about this, but this is the idea that we have different samples that we have collected, like let's say multiple studies. They're all put together and they're going to form the distribution of sample means that are actually going to represent the population. And why this is important is because if we have the population information, thanks to this distribution of sample means, we can use the Z-score to check where a specific sample falls within this distribution. And overall, again, if it falls within the normal range, which is what we consider 2 standard deviations, then we would say that our findings are non-significant. But if it falls on the tails, which we say includes the extreme scores, then we would say that our findings are going to be significant. And again, there is a more detailed lecture on this, but again, just so that you think about what is coming forward or coming ahead. But again, this is only true if we have a normal distribution. Otherwise, we cannot use any of the normal distribution ideas that we've discussed so far. So here is where we're going to finish with today's lecture. Again, here we are seeing a normal distribution that has this that pattern of Z-scores that we've been working with all of today. And again, we have a Z-score here that is splitting the distribution. And basically what the Z-score is going to tell us is that now all of this area is going to be considered normal, while this area is going to be considered extreme. These are the leftover scores that are not being represented by that Z-score and that go in the tail. And again, eventually, when we are comparing distributions, we'll be able to see or say whether a specific score in one of our statistics belongs to this distribution or another. And if it belongs to another distribution, then that might be an indication that we have significant findings. But again, if you felt a little bit lost on these 2 last slides, don't worry, because this is where we're going to retake the next lecture and we're going to go into more detail for this. Everything else though, please make sure you have a good handle. Remember that if you have any questions, you can email me. You can also book appointments with me and I'll be more than happy to answer any of those questions.